We are back again online, okay? And now we are starting our technical session. So we will be discussing about experimental, numerical, and eco-design approaches for sustainable automotive industry. And we have 4 very interesting talks planned for this next session. You will be hearing about new experimental techniques that we developed in the project, about the numerical formulation targeting fatigue we developed in the project, also about issues regarding effects induced by the manufacturing processes, okay, on high-strength chassis parts. And we will finish with this eco-design vision, okay, of the methodologies that were developed and were used in the project for reducing the weight in electrical vehicles and also minimizing the environmental impact. So I don't want to delay the session any longer. Let's start with the first talk, which will be given by Sergi Parareda. Sergi is a researcher at the Metallic and Ceramic Materials Unit at Eurecat. And I have to say, Sergi is quite probably the youngest doctor that we have in the consortium with us today, because he just defended his PhD thesis about a month and a half ago. So, Sergi, the floor is yours.
Okay, thank you, Lucia, for the kind introduction. And as we heard in the keynote speech by Henrik, the weight of the electric vehicles is mainly governed by the weight of the battery of these vehicles. In fact, this is not only for the heavy-duty vehicles, it can be also applied for cars. And in this case, the weight of the electric vehicles is increased in about 15 to 40%. So if we want to increase the range of these vehicles, then we have to reduce the weight of the other parts of the vehicle. And of course, it would be great if we can also reduce the weight of the battery. So then the main aim of the Fatigue for Light project, as mentioned, is to reduce the weight of these chassis parts in about 20 to 30%. That will give us a weight reduction of about 12 to 50% of the structure of the whole vehicle. In this case, we are mainly focusing on the chassis parts, since the body in white parts has been already optimized. And we can apply new materials and new techniques to reduce the weight of these components. In fact, when we are focusing on these components, we have mainly 2 main drivers. One is the fatigue properties, so we want materials with elevated fatigue properties, and also we want materials with a good formability to obtain these complex shapes, as we saw in the previous speeches. So the main point is that, well, we can have, right now we have conventional materials, conventional steels, and the main trend, as has been already applied for body in white components, is to move to advanced high-strength steels. However, we have to consider also the fatigue resistance of these materials. And in this case, we have a lot of different approaches. So we have to design the parts of the vehicle against fatigue, and we can focus on this low cycle fatigue regime, and we describe it by the strain life approach. Also, this high cycle fatigue defined by the stress life approach, and finally, this very high cycle fatigue. In this case, we are mainly focusing on the high cycle fatigue, so the stress life approach, and it's well known that the fatigue resistance of these components or the different parts of the vehicle it's mainly defined by the weakest link theory. So this means that the fatigue resistance will be governed or will be described by the material or the surface conditions, or, well, any point that can define or can govern the fatigue resistance and influence the fatigue resistance of the whole component. This means that we have to evaluate the fatigue resistance of all of these different conditions in order to properly design these components that have to deal with cyclic loads. So, and it means time and also money. So we need new techniques to reduce the testing time and also to reduce the costs of these tests. In the Fatigue for Light project, we mainly focused on 3 different techniques. One is the high frequency technique, where we use high frequency equipment working at 20 kilohertz, And at this point, we have these small specimens loaded at this very, very high frequency, and we can obtain the fatigue resistance in a very short period of time. But in our side, we have another strategy by using conventional machines, conventional testing machines. And the main aim is to monitor how the fatigue damage is evolving in the material, and in this way describe the fatigue behavior of the material. One method that we developed is the stiffness method, mainly based on the strain evolution, the plastic strain evolution in the material. And the other one that we have is the self-heating method. So the idea is pretty almost the same, monitor the fatigue damage, but in this case, by monitoring the temperature evolution in the material. So in this case, we'll focus these new techniques, in these two different new techniques that we developed in the project. And just to summarize very shortly how the fatigue damage, or how we consider the fatigue damage evolution in the material, we have this first movement of dislocation, or this first indication of fatigue damage. Then we have this micro crack initiation and propagation, and finally we have this macro crack initiation and propagation. This evolution is crucial because it's what we are seeing here by using these methods. In this case, we will start with the stiffness method, and in this method, the main point is to obtain the elastic response of the material at a given point, at different points of the test. And this test consists on applying a different blocks with different stress amplitudes and increasing the stress amplitude between each one of these blocks. Here you can see the testing conditions that are the same conditions that can be used in the conventional SN curve. And the new point of this method is to measure, as mentioned, the elastic response of the specimen between each one of these fatigue blocks. This will give us, will describe the evolution of the fatigue damage in these tests. So, and at the end, what we are doing is covering the whole SN curve by starting in very, very low stress and finishing the test when the specimen fails. The strain data can be obtained in different methods. By different methods, we can use, or we used, in fact, digital image correlation systems and also contact extensiometers. And the main point is that we want to use or to spread this method in the different labs. And these are common tools that can be found in the different fatigue labs. And this makes the method pretty simple. And in the end, what we obtain is this graph that you can see here in the right-hand side, where we have the plastic strain plotted against the applied maximum stress in each one of these fatigue blocks. And we can identify different regimes, mainly related with the fatigue damage that we saw in the previous slides, related also to continuum damage mechanics, the elastic fracture mechanics. And we can obtain the fatigue threshold, so the point where something happens in the material, and then also we can define the fatigue limit of the material. So we can obtain extra data and compare it to the conventional fatigue tests. So just to show a little bit the results that we obtained with this method, here you can see the results compared with the Stargaze method. So the fatigue limit at 2 million cycles obtained by the Staircase method, well-known method, conventional method, and then compare it with the stiffness method results. So here you can see that the results are almost the same. And also the good point is that, as I mentioned, we can get this extra information from the material, from this fatigue damage evolution. And we can process all of these data and also obtain a first approach of the SN curves. So here in the right-hand side, you can see the SN curve obtained by the ISO standard, following the ISO standard, and then the results for the stiffness method. So it's clear that maybe we have some slight deviations, but the main idea is to obtain further results in terms of the fatigue limit and also the SN curve in about 2 hours. So compared with the conventional test, where we are spending almost months, weeks or months testing, this is a huge improvement. So, but also the method is really useful to evaluate the effect of different surface effects, as we saw in previous presentations. To know the effect of trimming, for instance, is crucial for chassis components, and we can also use this method to evaluate which is the effect of these trimming processes in the different materials. And here, once again, the comparison between the fatigue resistance obtained by the stiffness method and also from the staircase method. And well, just to mention that we can obtain this data by using 2 or 3 specimens. And here also, another point that we are working is to not only to get the data from at the specimen level. So the next step is to obtain the data directly from the real components. So here you can see a frontal lever spring from a track. And the main point is that we are working on developing this kind of new devices to monitor the strains and get the data directly at component level. So on the other hand, we have this self-heating method, and the idea is all very, very similar to the stiffness method. But here what we are doing is monitoring the temperature evolution during the test. So here we are also increasing the stress amplitude between each one of these fatigue blocks. And by having this evolution of temperature plotted against the stress amplitude of each one of these fatigue blocks, these are the results that you can see here in the right-hand side, then we can obtain the fatigue limit of the material also in a very, very pathway and in an easy way. And in this case, we only need these different thermocouples attached to the grips and also to the specimen to evaluate the temperature evolution in the material. Here you can see the results for this method, for this self-heating method, compared to the staircase method. The results were also or are really, really similar between these two methods. And also here you can see the difference in terms of time. So 2 hours for one result against 1 month for one result. So this is really a game-changing strategy to develop materials and also for designing new components. And here also, following the same trend, we can obtain the SN curve for these materials by knowing the fatigue limit of the material. We can include 2 or 3 more specimens in this test and get the SN curve in a short period of time. And also these methods were developed for metallic materials, but also we work on develop these methods for composites materials. And here you can see the results for the rapid method and the conventional methods. And here also we want to highlight that these methods are really even more important in this case, because the testing frequency has to be reduced to avoid the effect of the strain rate on the fatigue behavior of these materials. And just to show that by using these methods, we can obtain, or by using this rapid method, we can obtain the fatigue resistance, or first approach of the fatigue resistance for composite material. And just to summarize and have an overview of all the work that we did, and to have the main ideas of these new methods here, just to show that we, as mentioned, we have these 3 different methods. This is stiffness method based on the strain evolution, pretty simple to apply in the lab, simply by monitoring the strain in the specimen. Then we have the self-heating method, also very easy to apply in the lab by using the thermocouples and to monitor the temperature evolution in the material. And finally, and especially to analyze this Vargas cycle regime, we can use these high-frequency tests to obtain the data at a very high number of cycles. And the main points, the 3 main points that you can see here in the slide, is that we can assess the the whole fatigue behavior in the high cycle regime in just a few hours by using a reduced number of specimens, usually by using only 3 specimens, and highlight once again that is an easy way to, that it's pretty simple to implement these fatigue tests in the lab at the specimen level, but maybe also at component level. And of course, it reduces the testing time, but also reduces the cost of the tests. So thank you very much for your attention.
Hello to everyone. I'm Sergio Jiménez, a colleague from Lucia, also working in CIMNE. And now I will start this new presentation of the technical session, talking about the fatigue numerical simulation throughout the Fatigue for Light project. I've structured my presentation based on this idea here, and basically I will be discussing about the uses of the numerical simulation within the environment of high cycle fatigue analysis. And so I've structured my presentation based on these 4 questions here: why, what, how, and where, trying to describe basically the scope for improvement in high cycle fatigue analysis from a numerical point of view, trying to identify which are the key features that must appear in a high cycle fatigue model. Then I will briefly describe the calibration process that we are following within the numerical model that we've been using in the Fatigue for Light project. And finally, I will be presenting you some of the case studies that we've been working on during the project. So let's start by presenting this scope for improvement. Basically, this is completely related with a presentation that my colleague Sergi has already presented, but now from the numerical point of view. So basically, when talking about high cycle fatigue studies, what we should think in is a really time-consuming test. As Sergi mentioned previously, a lot of samples usually needed, usually also a destructive test, resulting in a lot of time, a lot of money, so something to take into account. This also leads to this subsequent condition, which is that the study usually is limited to sample scale, because if we try then to apply all this study towards bigger cases like industrial demonstrators or complete structures like a chassis vehicle, then and when we try there to do such an in-depth study as the one that we perform at sample level, then this for sure would result in a lot of money, a lot of time, and something that it's usually not performed. And then we should also think in that these high cycle fatigue studies are just reproducing really specific scenarios. But what happens if we change the load conditions, if we change the stress ratio that we've been considering along with the experimental studies that we've done? What if we change the load mode that we applied in our capons, in our samples? But also, what happens if we undergo some manufacturing processes in the material that we're studying, like cutting, forming, trimming, like we've already seen? What happens then with the information that we obtain here? How to use that? And what happens at composites if we change the stacking sequence for some reason, or due to some manufacturing effects, some changes in the volumetric fraction occurs? Then the idea is that we should use this high cycle fatigue numerical model to tackle these ideas, and we should consider this high cycle fatigue numerical model as a tool to optimize the characterization, as a tool to eliminate those limits related with the scale, and also as a tool to generalize the fatigue study, meaning that we can address all these issues in a more optimized manner, let's say. And this results in this final comment from my side, saying that this high cycle fatigue numerical model must become a tool to be integrated within the fatigue analysis at all scales, not only a research scale, but also at lab and for sure at the industry level. So this is basically the, let's say, the scope for using this numerical approach. Now let's identify which are the key features necessary of on this numerical model technique. And let's see how this relates with the numerical model that we are proposing and using in the Fatigue for Life project. So basically you have here all the information, and now let's try to connect all this data. So while proposing a high cycle fatigue numerical model, we are thinking in a model that needs to capture the deterioration phenomenon that it's taking place in the material. And how we address that in our numerical model? Well, we built a constitutive law which is damage-based. This results in this type of stress relation, where we have here the damage variable affecting the material response. We need to distinguish between hidden and visible deterioration, because this high cycle fatigue phenomenon takes place for stresses which are below the yield limit. And so we need to somehow degrade our material for this type of stresses. And we do that by identifying two types of inelastic processes. And this one here is the one new coming from this fatigue constitutive model, which appears for stresses below the yield limit. And this type of law needs to account for strength and fracture energy degradation all along this fatigue process, let's say. And we do that by defining this FRED function, this fatigue reduction function, which is indeed reducing the strength of the material while applying the cycles, and dissipating the fracture energy in our material. Then we need to create a model, to define a model that it's able to generalize the fatigue study, in the sense that we need to account for nonlinear deterioration accumulation. So we need to make sure that if we change the load conditions, if we change the load conditions, then the model itself readapt to obtain the corresponding response in the material. And we do that by defining this reduction function that I was mentioning previously, not only as a function of the number of cycles, but also as a function of the load being applied, described through this stress ratio and the maximum stress. So changes in the load itself induces changes in the degradation path followed along the simulation. And of course, at the composite level, what we are using there is a series parallel rule of mixtures approach, where we focus the attention at the composite level. Sorry, not at the composite level, but at the component level. So we build up the composite response based on the component, meaning that if we change the component, the volumetric fraction or the stacking, we can automatically apply those changes in the composite response. And then we need to work towards an optimized simulation time from this numerical model. And we are tackling this issue by introducing an advancing time strategy in our numerical model, which basically transfers the simulation directly towards this inelastic response, this last part of the response in the material, skipping all these let's say hidden elastic or hidden inelastic process that takes place for the first thousands of cycles. So we go directly towards the end of the simulation, towards the crack propagation. Now that we know which is this model that we've built, let's move towards the use of this model. So I will be talking now about this calibration process that we followed in the Fatigue for Life project, and that needs to be done while using the numerical model that we are proposing. So basically what we do while calibrating the model is, first of all, focus on the monotonic characterization. And by doing that, basically what we are achieving is characterizing the yield strength of the material, the ultimate strength, the Young modulus, and the fracture energy of our material. And once we've calibrated, or once we've characterized this monotonic response of the material being studied, we move towards the fatigue characterization. And this fatigue characterization means indeed calibrating this fatigue reduction function that I've presented in the previous slides. And this characterization of this function is done by the calibration of 5 parameters here, which define the degradation being followed by the material while applying the cyclic load. And the way in which we do that is the approach that we follow is that we, together with this definition, this mathematical descriptive definition of the degradation in the material due to cyclic loads, we also have defined this mathematical representation of the Buller space. So basically, we are using exactly the same parameters in both expressions, and we connect, because they are connected indeed, we connect both expressions in such a way that by calibrating the parameters, or by calibrating this surface, this Buller surface, we are indeed calibrating the fatigue response in terms of the fatigue reduction function. So by doing this, which is quite an automatic process, we end up with the complete characterized model. And then it's time to build your model, the geometry, and run the case. That's it. So just to exemplify this, I've just prepared a small example in which I'm imposing a cyclic load, introducing a cyclic load in the material, and then after a few cycles, we move towards a monotonic load. And through this type of example, we will be able to see this strength degradation, fracture energy dissipation, and stiffness degradation processes that can be captured through this high cycle fatigue model. So in this first case, what you can see here is that we are applying 71,000 cycles of this cyclic load here, which is the normalized, well, indeed this chart is the normalized, showing the normalized stress. You can see here the effect of this advancing time strategy, and which allows us to skip all this regime where, of course, strength is being degraded and the fracture energy is being dissipated, but we can skip it because it's not visible at the material level, so we can compute it in another manner. And then we move towards this monotonic load, and you can see here, which is this stress-strain response for the material after these 71,000 cycles. So basically what happens in this material is that we have reduced the strength, and we also reduce the fracture energy of the material. If we perform exactly the same type of simulation, but now having this monotonic load after 77,000 cycles, what you can see is that the strength continues decreasing, and also the fracture energy. And then if we apply 83,000 cycles, what has happened is that the damage, the third region, the third inelastic region, has started. So together with the strength and the fracture energy dissipation, we also have a stiffness degradation computed based on this D damage variable that I was presenting previously. And the same happens when we move to 88,000 cycles. So strength, fracture energy dissipation, and also stiffness degradation appears. So now it's time to the application of this model in the case examples of the Fatigue for Light project. So we've worked at 3 levels. We've worked, first of all, at coupon level, aiming to characterize the model itself. And in this type of experiments, we've worked basically on 3 different types of simulations, which are pure fatigue simulations, reproducing the experiments done to obtain the SN curves. Something which is called residual strength experiments, which are like those that I've been using to introduce you the performance of the constitutive model. And then some experiments to study this loading sequence effect on the fatigue performance of a material while changing the cyclic load that is being applied. But just considering that this is the small scale case examples, I've just include here this pure fatigue or SN response experiments, okay? So basically what we are doing is introducing cyclic load all along the life of the material, and at certain point damage start propagating on the sample and it completely fails the geometry. And here you can see the comparison of the numerical, some of the numerical simulations in yellow with respect to the dots which correspond to the experimental campaign. So we are in good agreement for these two high strength steel and press hardened steel used in the fatigue for life project. Then moving towards this second scale of analysis, which corresponds to, as Lucia mentioned on her presentation, studying the manufacturing effects on the fatigue response of a material. We've performed several types of numerical simulations, trying to study from a numerical point of view the trimming effects, punching effects, forming. So let me just share with you some of the results to really share with you which is the approach or which is the way in which this numerical model is able to take into account this sort of effects. So basically, in this particular case for the trimming, what we've done is changing the roughness, the surface of these geometries, accounting for this change in roughness coming from the trimming process. And by doing that, this has an effect on the fatigue response in the material. So we have different pattern of crack observed, different amount of cycles, and this correlates perfectly with the amount of cycles observed experimentally. We are not taking into account here residual stresses, and this may explain that that we are obtaining higher values, higher fatigue life compared with the experimental results. But we can, of course, take into account residual stresses, and this is what I'm showing here in this punching example. So basically, we have the information of the residual stresses in this punch area, and so we incorporate this information in our simulation, and by doing that, this is the effect that it has on the evolution of the crack observed along the simulation. And you can see here the final failure of that sample obtained after 81,000 cycles, which matches with the experimental results obtained for this type of sample. And then with respect to forming, basically what we've done here for this particular scenario is applying a tensile load, which induces some plastic strains on the material. And then this sample, for this sample, we applied a cyclic load up to the failure. And then, well, this is the approach that it's being followed experimentally, and we reproduce that from a numerical point of view, and we're obtaining nearly the same results experimentally and numerically. So good news, because the model is able to capture this type of effects corresponding to fatigue, affecting to fatigue. And now we move towards the last scenario, where we are to the last scale, where we are just working through these industrial demonstrators. And we've been working with three types of industrial demonstrators. This lower control arm, we have also a wheel and a crossbeam member. So starting with this lower control arm, we've been studying this steel solution made of CP980. And we've been studying numerically two types of fatigue experimental tests. So in this first one, we are applying in this arm, this branch of the lower control arm, this load here, and we are constraining those points in the geometry, and then we applied the cyclic load. And what we obtain is we can capture similar, well, not similar, we capture perfectly the crack pattern obtained experimentally, identifying this first crack and then the secondary crack exactly in the same manner in our model, and also in terms of number of cycles. So this was pretty good, but we also performed another simulation for another case study for this steel lower control arm, where now the force is being applied into this element here that it's being welded to the rest of the lower control arm. And this is the type of result that we are obtaining from the simulation, again, capturing the type of crack patterns observed experimentally, and also with a good agreement in terms of number of cycles. Then, with respect to the study that we've done for the hybrid component, for the hybrid lower control arm, the numerical campaign has been limited to the misuse study, meaning that we are just studying here comparing the stiffness that we are measuring numerically with the ones that is measured experimentally. But we are in a good agreement also with this version of the lower control. Then moving towards the wheel, we've been simulating this bending experiment for the wheel demonstrator for several bending moments being applied, and from that we again capture the type of crack pattern observed experimentally, and we perform similar studies for other, as I was mentioning previously, for the other bending moments, and this is the correlation between the experiments and the numerical results for one specific demonstrator made of CP800. We've done similar experiments for other thickness and for other materials, obtaining also good correlations. And then finally, with respect to the crossbeam member, we've been working with this model here, and we've been characterizing both the monotonic, studying the monotonic response and the fatigue response in two directions, in the Z direction and also in X direction. So here you can see the response obtained numerically compared with the experimental one for the crossbeam member working under monotonic load with good correlation, better one under Z loads, but both pretty good results. And then here we have the results obtained for these fatigue loading conditions. So basically this is the one corresponding to the Z loading direction, where experimentally they detect this crack appearing in this region after 70,000 cycles. And here we have the crack in more or less in the same region, and this is the type of propagation that we were obtaining for this particular scenario. And here you can see the correlation for several loads being applied in the crossbeam member. Just to mention that these two correspond to runouts of the experiment. Okay, we are measuring failures from the simulation point of view, but they are taking place after the maximum number of loads being considered by the industrial partner. And then we have the fatigue response in the other direction, in the X direction. No, in the X direction. This is not correct. This is X, not Z. And from experimental point of view, they detect. This is work done with Gestam. So Gestam detect the crack in the demonstrator level in this region here, which is the same that the same type of crack that we detect at simulation level, and you can see here the correlation between simulation and also the experimental results. And just to finish, I've just draw some conclusions here to summarize the key points about the numerical model that we finally created and applied along the Fatigue for Life project. Just to say that, as you may notice, this is an easy to calibrate model. Most of the process is done in an automatic way, at least for the fatigue part. And good news, is based on SN data, so more or less everyone should know how to calibrate it. It allows a continuous description of the problem. So once you've calibrated, you can change the load that you've defined or that you are used to create to build the SN charts, and you can still use the model. It also allows to describe the crack path, which is something that it's not usually that cannot usually be done in commercial codes. And also good news is that we can do this not only at coupon level, but also at demonstrator level and in general, in any general model, because it's an inherent property of the model that we built. And then just to mention also that this is an optimized tool. It's been integrated in an open source parallelized code, and we've also included an advance-in-time strategy together with the model. And just for you to know, the simulations that I was showing previously, they are in the order of minutes or hours, the maximum. So really competitive in terms of time. So thank you all, and I will be glad to answer your questions after my colleagues' sessions.
Now Magdalena and me are going to present about the eco-design aspects of, well, that we took care during the Fatigue for Life project. So we've been listening about all the technical aspects that were studied during the project, and now the eco-design. And I'm going to start with a bit of reminder on the definition of eco-design. Eco-design, according to the European Environment Agency, it relates to the integration of environmental aspects into the product development process. And this means that this means that you have to anticipate them and minimize or try to minimize the negative environmental effects through the application of life cycle thinking, and including all the life cycle stages of a product or service during the lifetime of this. Also, without losing any function, the quality of the products or materials, or the technical performance. Along with this, the European Union has been addressing the challenges to reduce the automotive industry environmental impacts, and in pursuit of decarbonization as well. So following all these facts, the definition of eco-design and the goals that we have in the European Union and worldwide to reduce environmental impact and to reach zero emissions world, in a circular world, Eurecat has developed a methodology to apply eco-design to different products, processes, and services. In this sense, the methodology that you can see on the screen, very briefly explained, is going to be, for this methodology, we considered 4 very intuitive and iterative process. These 4 steps that were included in the methodology follow the plan, do, study, act methodology that is widely known. So at the first, we evaluate in a preliminary assessment and identify at the same time the hotspots and life cycle stages that should be taken into account in the study, and where we should focus our efforts in. Then the second step helps us define the strategies, the most properly eco-design strategies based on what we found on step 1 on this hotspot. So to focus on those hotspots that we found. Then step 3 is the readaptation, if needed, of these eco-design strategies to the technical part and the technical procedures. Also to economic aspects as well, to make sure that these strategies are viable and feasible to apply to the design of the product. And then as a step 4, we came up with a definition of specific actions, not only broad strategies, but specific actions that were going to take place during the development of in case of fatigue for life, the demonstrators. So for these definitions, we followed the European Union categories for circular economy of design and production, the optimal use of resources, the recovery of value and support, and also with the goals of the Fatigue for Life project. And we, as a team, we worked to define the most suitable strategies that we could follow through. Then we evaluated where these strategies would have a greater implication in the different life cycle stages. And after that, as a step 3, we realigned the strategies to the technical aspects. We make sure that these are viable and feasible, and define a set of specific actions that Magda will explain a little bit on.
Yes, thank you, Violeta. So from strategies to actions, so for beneficial material selection, we were focusing on the using of recycled and recyclable materials for different demonstrators. And in particularly, we used aluminiums with high content of recycled aluminiums. For the material selection, again, also very important was the reduction of critical raw materials from alloys. Considering the origin of the materials, we wanted to look more in like from a helicopter perspective, considering what the material choice and the origin would affect the entire life cycle of a vehicle from the environmental point of view. For design for lightweight, the next strategy, the focus was here to use of lightweight materials to reduce the weight of electric vehicles. And for this particular case, we introduced hybrid solutions where we had a composite part together with the aluminium part. So it was a combination of this. Then, if it comes to introducing optimal design for lightweight, this was done through considering what type of vehicle the components are designed for and what is its use pattern. For the numerical strategies, the focus was to use numerical modeling to optimize part design, and among others, the focus was on topology optimization. For design for maintainability, we introduced optimal design for life extension. And in this case, one of the solutions we had was to integrate optical fiber sensors into the composite part in our hybrid solution in the future to be able to serve data for the fatigue models or also to be able to understand better when to schedule maintenance like repairs or when to recycle. For design for end of life, we adopt a design for recycling approach, and here we used a principle in our hybrid solution. We used the principles of induction heating, where we were able in a very effective way to separate the composite part from the aluminium part. And for the value return, we adopt the design for disassembly approach by including the use of joining elements that can easily be removed. So for each of these actions, we made the detailed evaluation considering our physical demonstrators. In the next slide, please. Yes, I will present in details how we did it for just one solution here or one action that is for use of lightweight materials to reduce the whole weight of electric vehicles. So to the left, we can see what kind of criteria we used, and also we have our 4 physical demonstrators here, which were considered. And for instance, for the hybrid solution, the advantage was, or this kind of approach and action was applied to 100%, and with the advantage to reduce weight, and we were able to achieve it, and with about 30% of weight reduction for the hybrid lower control arm. We had some challenges with the durability here as well, so it was not only very smooth. But the next step was to measure this kind of actions from the environmental point of view. And this, for this, I will give a word back to Violeta. Thank you.
To analyze in detail what were the results of applying eco-design to these different demonstrators, what we used was life cycle analysis. So we calculated the environmental impact of these demonstrators within an electric vehicle, a hypothetical electric vehicle during all the manufacturing stage, the use stage, and the end of life. And then we compared the results from the beginning and then after applying eco-design. So these are the goal and scope that we follow for the application of life cycle assessment, which includes all the inputs of material and energy for raw material extraction, for the manufacturing of different auto parts, for the vehicle assembly, then for all the impacts for the use stage, and then consider an average end of life for the vehicles. Also considering all the outputs too, as emissions or environmental aspects. The functional unit that we considered was 1 kilometer that is driven by an electric vehicle. And for this, we considered a lifetime driving distance of 180,000 kilometers. And then we also compared it with different options of vehicles. We compared between an electric vehicle, combustion vehicle, and a hybrid and a plug-in hybrid vehicle. But to show you just a little bit of our results, we are only going to show the battery electric vehicle results, and only on one of the environmental impact categories to summarize the results. But we have the results for all the different impact categories, not only global warming, as you can see on the screen. So for global warming potential results, on the crossbeam member, we had a reduction of environmental impact of 31%. Then for the wheel, we saw a reduction of 19%. And for the lower control arm, we have different options because we had different alternatives of steel and also the hybrid solutions. But the greatest reduction was an 8% of reduction on environmental impact. Although, if we considered all the other environmental impact categories, we can see up to 65% reduction on the impact, for example, for the lower control arm, or 57% for the wheel. And this is just an example for you to have an idea on the environmental impact results of applying eco-design throughout Fatigue for Life project. What we found after applying the eco-design methodology was that this was a very good exercise to boost teamwork, to participate, defining the strategies, the specific actions that were taking place during the Fatigue for Life project. We also enhanced the implementation of technologies and procedures when we included all the life cycle stages of the vehicle. When we considered all this, we could make better decisions also for the processing of these materials and the components. And also another plus of using this eco-design methodology is that it addresses environmental perspective in a continuous way, because you can evaluate the different materials and do some arrangements to make it even more sustainable or with less environmental impact. We look forward for your questions and comments in the section after this session.
Okay, everybody, thank you for your resilience, for your resistance, endurance, having reached this point in our session today. This is the moment where we dedicate some minutes to the Q&A session. We have a slight time delay, so we won't have time for a lot of questions. But I do want to ask a really quick question for each one of the speakers in this session. Okay, so since the first talk was given by Sergi, let me just ask you, Sergi. You've shown us some super interesting developments regarding the rapid testing methods, okay, for fatigue. But can these methods be applied at component level, or should we stick only to coupon level?
Thank you, Lucia, for the question. Yes, I as mentioned it very fast in the presentation. We are working on to apply also these methods at component level, since most of the chassis components are tested and in the benches of the labs and so on. It will be also crucial to have a tool to assess the fatigue resistance or to validate the fatigue resistance of these components in a fast way, and also will help to reduce the testing time of the development of all of these components. So yes, the main idea is also to, or it can be also, these methods can be also applied to component level, and in this way reduce the development time of all of these components. We did some tests for some components for heavy duty vehicles, and in the coming months, hopefully we can keep working on this method at component level. Thank you for the question.
Okay, well, thank you very much, Sergi. Let's go quickly to the next speaker to the talk on numerical modeling. For Sergio, I have a question here that I would like to give you the opportunity to answer. Have you tried using random loading rather than the constant amplitude loading in the numerical simulations that you've been doing in the project?
Okay, I will try to answer. The main issue here is that a completely random load cannot be used on this model, just because we need first to define the cycle prior to specify which is the degradation effect that this load introduces in the material. So we need some kind of stability for some few cycles, let's say. But once we've established this short stable cycle, then we can change the load dramatically, and we can continue, of course, predicting the degradation. So basically, what we've done in the context of the fatigue for life model is working in this loading sequence effect test, where we change the load being applied. So we do not apply just a constant cyclic load, but different load blocks. And we've seen there that there is a good correlation between the numerical results and the experimental results. So yes, but under certain circumstances.
Okay, thank you very much, Sergio. Let's move on to the next speaker, to Eric from LTU. Just a question about the effect of forming and shot pinning, these different strategies that can help improve the surface finish for coupons, for components. Can we model these types of effects?
That's something we will work with right now. And I think sort of the same approach that we have done might work there as well. Try to understand the process as good as possible. Try to model things like residual stresses and damage, and then use the same approaches here. Shot peening is a bit special because there we have very local effects. It's a ball that's hitting the surface, but also studying this in detail and try to bring it to the component scale, the effects of it, I think is the way forward here.
Okay, thank you very much, Eric. And just a very quick question for the eco-design team, I would say, to both Violeta and Magda. I would like to ask you regarding the methodology that you focused on in the project. Is this methodology applicable to other types of vehicles and maybe to other products?
Yeah, when we first developed this methodology, we were aiming for the application of it in any kind of vehicle and any kind of product. And we are trying to prove that this is applicable. So far we've applied this methodology in this project and also in another project more related to batteries for electric vehicles. But it's still the same sector because we're still talking about batteries and electric vehicles, components from electric vehicles. So, but yes, the methodology allows all this tuning of the methodology or the application of the methodology to different aspects. Since the description of the strategies can be aligned to whatever focus you want to give or sector you want to try and apply it, then it allows this flexibility of applying it to any sector. But we are really like excited to try it in other sectors as well to have an evidence that this works.
Yes, especially if this kind of methodology to develop it's very time consuming. So it would be very efficient to, you know, to be able to use it in different applications.
Also, from the project points of view, I mean, using the work done in the project, you know, giving it the maximum exposure and outreach possible, I think would be really, really wonderful for the future, right? Okay, thank you to all of you. Thank you also to the attendants. Let's take a very short break. Just 5 minutes, okay? It's 11:48 right now. I'm not going to say 2 minutes because we can't even go and grab a glass of water. But let's meet at 5 minutes past 12, and we can start with the roundtable discussion, which I definitely want to invite you to stay tuned because it's going to be a very interesting discussion, okay? Okay, nothing more from my side. Let's go and grab a coffee and see each other at 5 past 12. Thank you.